He's professor for applied mathematics at the University of Washington. He started at actually the University of Washington and gotten his PhD in applied math at the Northwestern University. And one of the very exciting topics that he is investigating for the last few years is how deep learning models can actually discover properties such as coordinates or underlying equations in dynamic systems in a data-driven way. And this is what his talk will be about today. So please, Nathan.
Great. Hopefully you can hear me just fine. Yeah, Mario?
Yes, everything good.
Great. Hey, hi everyone. Hope you're all doing well. Happy summer. I just want to let you know that yesterday in Seattle, which we never get this, it was 42.5 degrees Celsius. It was a scorcher. So that was 108, like it's some record. I did not melt. I was a little worried. But hopefully you guys are enjoying your own summers, and thank you so much for being here. What a great set of talks so far today. I really enjoyed seeing what people are working on. So I'm gonna talk here about deep learning. Obviously, many of us are doing things around deep learning, but this is going to be a very focused on thinking about the joint discovery of coordinates and dynamics together. And this is where it's going to lead up to in the talk. And so hopefully I can make some of these points clear as we go. All this work really I'm going to talk about is with my colleague here at the University of Washington, Stephen Brunton. And really we're going to feature a lot of the work of our students and postdocs that have been doing research along this direction. So I'm going to start here, which is part of what we want to do with data is we want to start with an input data stream, and we wanted to really start framing it using targeted use of neural networks. In other words, we want to be able to interpret what we do at the end of this, and we want to be able to understand the entire discovery pipeline, so in sort of simple structure. So we think about taking the input data, finding coordinate transformations to represent the dynamics and to be able to come back out. So this autoencoder structure becomes this important architecture for what I'm going to talk about throughout this talk. And I want to kind of contextualize this in terms of what does it mean to have good coordinates, because that's obviously a little bit of a subjective term when you say I want good coordinates. And so I want to try to at least explain what I think I mean by good coordinates. And you know, it's just one person's opinion, so you don't have to agree with this. It's just more a matter of one direction you could take about good coordinates. So we start here because this is actually in my opening slide. It was basically the night sky, and what you're seeing here is the retrograde motion of Saturn and Mars. So Mars is in the foreground here, taking these sweeps across the sky, and there's Saturn in the background. And this was the big grand challenge in physics, right? For many, many centuries, millennia, is to understand the motion of the planets. And so this is, you know, kind of an achievement of humankind, is to sort of start to understand what are the fundamental principles behind this. And we've been observing the night sky ever since we could write anything down, certainly, and long before that, we were curious about this. And in fact, the first successful theory about this, I would say, is really as a predictive theory, was the doctrine of the perfect circle. It came out of the 2nd century AD, Alexandria, Egypt, which was sort of the intellectual center of the world at that point. And Claudius Ptolemy sketched out this concept of how to construct a model for describing the planetary motions, which is this idea of circles on circles. And you have these beautiful sketches here. For instance, this is a Renaissance sketch of this concept of this doctrine of the perfect circle. And the idea was the Earth was the center, and you could describe the motion of all the planets as circles upon circles. It's actually kind of interesting. If one way to think about this is the earliest version of a Fourier transform, right? Decompose everything into a set of frequencies, and you can do a nice job with representation. And it was a very successful theory. In fact, it's kind of like the Roman Empire of theories. It was from the 2nd century AD all the way to about the 1500s or 1600s before it finally came down. And what brought it down? Well, a series of experiments and works, and you have Galileo, Kepler, Copernicus, all pushing and advocating for this idea of the heliocentric coordinate system. So the biggest advance here for understanding gravitation, in my view, was first getting the coordinate system right. Once you understand that if the night sky, these retrograde motions, is just a matter of viewing it from a coordinate system, from the Earth coordinate system, and if you transfer it to the heliocentric coordinate system, everything sort of unfolds in a very natural way. And it was the advancements that came at great cost, by the way, to especially Galileo, right? He was tried for this, and he recanted all of it under house arrest for the rest of his life. But the truth won out here, and eventually it leads 100 years later or so to Newton, with the right coordinate system, is able to then posit the F equals ma physics that we have for understanding gravitation. By the way, that wasn't the end of the story, right? So we get this model, and then in the early 20th century, we start noticing that, well, something's not quite right. There's some discrepancies here, and that is also having that refined data on planetary motion allowed us to understand that the model wasn't quite right, and allowed for the development of general relativity by Einstein. And I put over here on the right a picture of, this is your, if you don't have someone's picture, right, you just put this little generic little picture there. Somebody, sometime in the future, when we get better measurements, will probably say, well, general relativity isn't quite right. Here's what the real theory is, right? So we keep making these progressions largely as a consequence of having better and better data. In fact, really what allowed a lot of this to go forward as well was that Kepler had access to Tycho Brahe's data. And that made a huge difference in him laying down his planetary laws of motion. In either case, this is the idea. The discovery paradigm that's here is exactly what I want to try to advocate throughout this talk, which is there is a coordinate transformation from the data. Can I find a mapping to the right coordinate system? Now, once I find that right coordinate system, now I can properly contextualize it. So this isn't from the Earth-centric coordinate system to the heliocentric coordinate system, then finally allowing me to discover the dynamics, which is in this inverse square law. So this is sort of historical in nature, but it's going to just reflect the underlying philosophy of this entire talk. So let's talk about the mathematical formulation I'm going after here. It's going to be based upon these here. You're going to have measurements of a system. And one of the things that's really important in my view, at least, and this is just, again, an opinion, is just because you measured it does not make it the right variable. And I think that's a really important point. We have sensors, we measure things, and we try to construct physics models, and we're getting better and better sensors all the time. And ultimately, this is what's actually revolutionizing our model discovery possibilities. Not that we're just smarter and have better regressions, that's one of it, but really it's because we have the data and the measurements from these improved sensors to do this. Biology is a perfect case where it's like what people can measure in biology now, it's just absolutely unbelievable. So we have a measurement at specific time points. I'll focus on time-dependent problems for now, but I'll talk about boundary value problems later. And I don't necessarily measure the state space directly. I measure y, which is some version of x through some measurement model. I always pick up noise in that measurement. And then, of course, the dynamics itself is prescribed by some function f. So I have dx dt equals f. It's got some parametric dependence. And so here's the goal. From the measurements alone, discover h, f, theta, all of it. This is a terribly ill-posed problem. In grad school, I always was told if the problem's ill-posed, you just go do another problem, right? I mean, it's ill-posed, so you can't solve it. So you go look elsewhere for a problem you can solve. Otherwise, you're going to be doing your PhD forever. But now that I'm older, I realize that actually this is fantastic. If I start doing things with statisticians and computer sciences and machine learning, if it's ill-posed, it's not a big deal. All you have to do is impose constraints and regularizations to make this problem solvable. So what are the constraints I want to bring to the table here to solve this ill-posed problem? I don't have enough information to do it. And so what we're going to advocate is one really critical set of constraints here, or regularizations. And that is around the idea of interpretability and parsimony. So for us, the ultimate regularization tool we're going to use, and I'll show you this, is going to be parsimony, which is how can I represent the physics in this coordinate system with this, in some sense, the smallest number of terms. These concepts go all the way back to William of Ockham, where he proposed this idea of, in some sense, nominal representations, and it's really built out by lots of other people, including Pareto, where we have the Pareto front. So I want to sort of, in some sense, solve that problem where I minimize the number of terms and the dimensions needed for that. So in my view, that's the ultimate physics regularization. So let's start here with linear models. So what do I mean by linear models? Remember, I have this pairing of coordinates and dynamics. So what I want to do is say, well, maybe I can find a coordinate system to make the dynamics linear. By the way, even if the dynamics is nonlinear. And this goes to the emerging ideas of Koopman theory. So here's the idea. Let me give you a simple ODE here. Here's a 2x2 nonlinear ODE. Right? This is not that difficult, but look, if I transform variables into y1, y2, y3, defined as follows, the system's linear. So the whole idea of Koopman, who worked in the 1930s and was really advocating this for quantum mechanics, was to say, don't work with the original state space, transform it into a new variable where that variable now, the dynamics in that variable is linear. So this is exactly what we're going to do, at least initially for models. And so we're going to start learning how to make this transformation. In the previous example, I could write it down, but this is actually generically pretty hard to do. And so what we're going to do is use neural networks to help us find linear transformations. And this is work with Bethany Lush, and Bethany's now at Argonne National Labs. And the idea is to start with my initial input X, learn a transformation to Y, and come back. The question is, what do I want to have happen in Y? In Y, when I go from YFK to YK plus 1, in other words, I could take time step forward in time, I want it to be a linear mapping. So I want to find a linear operator that maps me forward in time. So that's what I mean by finding a Koopman operator here. So how do we do this? But, well, I'm going to show you how we train this. In fact, I also want to compress the dimension down to sort of the intrinsic dimension of the dynamics itself. It's always easy to take a neural network and go to very high dimensions and get a model to work, but I want an interpretable model. So I want to crush this down to the smallest dimension possible to maintain interpretability. Well, so a lot of these models, in fact, in the pendulum, the simplest example, the nonlinear pendulum, not the linear pendulum. So the full theta dot equals sine theta, you have a continuous spectrum. So one way to augment what we have here in the setup is to build a parametrization of that continuous spectrum. So you can still make this thing come down to theta theta dot and the dynamics, but now the linear operator is parametrized by the frequency. And when we do this, we can actually take the fully nonlinear pendulum. So here it is. So as you start to get larger and larger oscillations, it becomes more and more strongly nonlinear oscillations. And we can take all of this and collapse it down into a linear model. And essentially, these are your eigenfunction transformations, your nonlinear eigenfunctions associated with this nonlinear pendulum. So essentially what we did is we linearized the pendulum all the way up to the saddle, right? So the whole thing is a linear model up to there. And this is how you would do this, is use the neural network to learn that transformation. We can also do things like flow around the cylinder. Again, this is where von Neumann vortex shedding is happening behind this cylinder. So it's a nonlinear dynamical system back there. It's low rank. And so we can essentially learn an embedding and a transformation to make the dynamics behind this thing purely linear. Okay, so this is just about finding the right coordinate system. And we do that using our neural networks and it's a targeted use. The only job of the neural network is to find this coordinate transformation and allowing this thing to become linear. We took this idea and considered much more difficult problems. And particularly what we did is we think, okay, can we do this for generic partial differential equations? And so what we did is we took something like the Kurimoto-Shibashinsky model, which, by the way, if you've studied that, you'll know that it has very complex dynamics, a lot of spatial temporal chaos. It's a pretty rich model with that's been really well studied, and we know that there's a lot of interesting dynamics that comes out of this. And we asked the question, would it be possible to learn a transformation in which the dynamics of this Kurimoto-Shibashinsky becomes simply a linear evolution dynamics? And in fact, with Craig Jin here, we in fact did that. I was actually really surprised we were able to do this. You know, we started off with some simple models, PDE models, we knew we would probably be able to do, but we were able to do this here, which is we had a much more sophisticated neural network architecture, but it's conceptually the same, which is start from your measurement space, learn a transformation to a new latent representation where the dynamics in that representation is linear. And what you're looking at over here is a bunch of different initial conditions for the full PDE versus our neural network approximation, where the dynamics in this here is linear. And this thing nails it. So it's quite remarkable how powerful this idea of Koopman operators and Koopman embeddings is. And it's a way to represent dynamics. It's one way to do this is by taking that neural network, having you learn for yourself a coordinate system where linear dynamics occurs. Okay, we can also just make linear dynamics happen in time by using the same concept to warp time series data. So here's some time series data. For instance, this is work with Henning Lange, where it's quasi-periodic actually, and it's like power grid data is like this kind of data here with. But if you do it a Fourier representation, it costs you many tens and hundreds of Fourier modes. But if we just took something like this, took a neural network and learned a transformation to turn this into the smallest number of sines and cosines possible, and then do a fitting in that coordinate system, this allows for this very efficient representation of these dynamics that you might see in a lot of systems where quasi-periodic behavior happens. So, and in fact, such a constrained Fourier Koopman decomposition beats all of these leading machine learning methods like LSTMs, Blue Equistate networks, which are often sold as they can beat everything. Well, you can't beat some of these nice sparse representations, in my view. And we have the data here, and we have the method to prove that. So we're kind of excited about this because this tells me at least that a lot of our physics intuition and thinking, when it's brought into the right architecture with neural networks, is going to probably be better than just throw everything in a neural network and train it. And we have interpretability on top of that, right? And so you can do things like this. Here's a full PDE, and if I look at the low dimensional, like just do a dimensionality reduction on this flow physics of a computation, I can basically collapse this down and then just do this Koopman projection. And so what you're looking at the bottom is actually a representation of the truth up there, and it's actually incredibly accurate as a reduced order model. And we get this, so I can give you the future state solution trivially because I just represent it. I have the representation in terms of a set of learned Fourier modes in a new coordinate system. Okay, so that's one approach, which is to think about embedding things in a coordinate system where things are linear. It could be that I actually would like to keep the dynamics nonlinear because, in fact, nonlinearity dominates what I see, and I would still like, though, some governing equations that represent this well. So here, I want to talk about this method we've developed called the sparse identification of nonlinear dynamics. All this is, mathematically, is AX equal to B. But the way it works is it's really nice. It's sparse regression on AX equal to B. I take time series data, so I know that I'm looking for a model x dot equals f of x. If I measure x, then I can differentiate it to produce x dot. So that's B in AX equal to B. That's over here. The matrix A itself is a library of candidate right-hand side terms. What kind of dynamics could be in the model? So right behind me here, I don't know if you can see my little bookshelf and you can see me here, but I have a bunch of books learned books on physics and math. And any one of these books has tons of governing equations that we all learn in our educational system. And so I could say, well, I know how to construct a library of things that I've seen in a lot of different kind of physical and engineering systems. So I'm going to make a library of all kinds of behaviors that I might see here. That's A. What X is when I solve AX equal to B, X itself is the coefficient in front of every library term. And so what we do here is promote sparsity. We say, try to make as many of these terms 0 as possible and only keep as minimal set as possible. And in doing so, what you do with this sparse regression is zeroes out most of the library terms, except for the ones it really needs to fit the data. And lo and behold, here are the non-zero elements. So if I give it Lorentz data, it actually learns that that is in fact the right-hand side. So it learns the Lorentz system, even though I just gave it time series data. So you learn the governing equations that produced the data in this architecture. We can generalize this concept to learn PDEs. So you give me spatial temporal data, and all I give you is snapshots, spatial snapshots in time, and I can tell you the PDE that govern the generation of that data. So that's the idea behind this. This here was done by Sam Rudy, a former student of ours. And by the way, all the code of everything I'm talking about, all of it's up on GitHub. It's all available for you to use if you want to play around with it. So this allows us to discover governing equations, ODEs, PDEs, and so forth. Now, I'm going through this fairly quickly, right, for time, but one of the more important aspects of what I think this would be used is in this idea of discrepancy modeling. Note it's a simple regression, but most problems we look at, we actually know quite a bit of physics. So why not take what we know and just learn the missing physics that we have? Now, why is this important? Because things like the digital twin, so for instance here, I have a simulation of a robotics arm, and these are very simple equations to write down in the Platonic view, like here's the masses, here's my weights, here's the length of these arms. But the fact of the matter is, this real robot for precision manufacturing, this model is not accurate enough to capture this real robot arm because, in fact, there's frictional forces that each joint has a little bit of stick to it. So what you could do is say, well, I know my governing equations, I know parts of it to be true. I can use the same regression framework that I just showed you here to say, build a library of the potential missing physics terms, do the regression, and now learn in an adaptive way what the difference between these two models are. So I think this is actually a really nice way to do physics where you say, I have partial information about the physics, and all I need to do is learn a little bit more because my model's not sufficient. It's very rare that we walk into a problem anymore and we know nothing. Most of the time we have a lot of partial knowledge, and so this framework is very well suited for partial knowledge. Okay. So far, I skipped a little bit of what I actually talked about in the title, which is how do I discover dynamics and coordinates jointly? Notice that what I did here so far in the examples, I already knew the right coordinate system or I had it close. So what I want to now talk about is how to integrate this all together into a structure that allows you to, what I like to call, do GoPro physics. You film an experiment, you film physics, you have HD cameras watching what happens in an experiment, and how do you learn physics from this? This is exactly what's going on in biology, right? We can now do these amazing imaging, dynamic imaging techniques, and this is how we're starting to build models directly from collecting such data. So here's how we propose doing this. This is work done with Kathleen Champion. She just graduated last year. And what we did is we took this autoencoder structure. So you take measurements, you try to learn a new coordinate system, and in that coordinate system, you impose this SIMD architecture. So this is the entire structure of this thing. So what does it mean? From your measurements, you learn a coordinate system where you can parsimoniously represent the physics. That is what we're after. So let me give you the example of this, and I hope this is hopefully very clear. If I videotaped a pendulum and I gave you that data, what you would have is a video in pixel space. It's extremely high dimensional. That's what X is. I give you a video of a pendulum. From the video, what this learns is theta, theta dot. I don't have to even tell it what it is, because in theta, theta dot, in here, theta dot, double dot is equal to sine theta. That is the kind of representation that this allows you to do. And by the way, going back to the original planetary example, given your observations, and unfortunately, it's been hard to extract out a lot of data with planetary motion to actually get it. But the idea would be is from the observations of the night sky, it would learn the heliocentric coordinate system and the inverse square law directly. Inverse square law I'd learn here, heliocentric coordinate system there. That's the concept. We've done this on a bunch of examples. The bottom one here is the one I just talked about, is just say from a video of a pendulum, it actually learns the pendulum equation and the coordinate transformation. So this is this joint pairing. In fact, they have to come together. And I always think about this nowadays, which is we often underestimate how important the right coordinate system is. And that's probably actually the most important thing of all, is what is the right variable representation I want. By the way, we can generalize this same kind of autoencoder structure, learn what are called normal forms, right? So there's these underlying bifurcations that happen in all kinds of dynamic systems. We could just learn that representation directly from the data. So what this allows us to do is learn the underlying parametric representation of the data. Okay, so this just got put up on the archive. We can also take the same kind of structure and learn what are called deep conjugacies for periodic dynamics. So there's a lot of infrastructure that can be used in this kind of very generic autoencoder dynamics in the middle. And so I'm not going to go into detail on any of these. I just want to say that it's very modular and allows a lot of flexibility for learning a lot of conceptual pieces in this discovery pipeline. Another piece of this that's just kind of interesting is in this coordinate system you learn, if I learn theta dot is sine theta, that's somehow generalizable, right? We can, in other words, if I learn F equals ma, it not only applies to one system here, it applies to a bunch of other systems. Except for every other system, I have to learn a new coordinate system. So anybody who's taken statics and dynamics, which are classic engineering courses, most of the goal of those courses is to learn coordinate systems for your free body diagram. So for every system, you have to learn a new coordinate system. However, we are trying right now, within a given system with parametric dependence, can we learn a parametric representation of that coordinate transformation? I think we have some ideas about how to be able to do that, but that's something we are definitely looking at. I'll finish up with some last thoughts here, which is everything I've talked about is time dependent, but there's no reason you can't bring all of this architecture onto boundary value problems. So here you would just trade this out. And this is work with Dan Shea, which is I take input measurements, I learn a coordinate transformation to learn underlying boundary value problems. So I might have a system, I don't know the governing equations. I can learn the governing equations of some boundary value problem or some static type problem through this kind of same architecture as before. And even more importantly with Dan, what we're able to do is learn Green's function representations. So for those of you who do have worked with Green's functions, right, it's the fundamental solution to a problem. And so the problem with nonlinearity is superposition no longer holds. What this deep green architecture allows us to do is make a coordinate transformation to a linear system, build the Green's function there, and then come back out. So it allows us essentially a nonlinear Green's function representation that I think it can be very important for a lot of different applications across the engineering sciences. All right, so that's it. So for me, the conclusion is pretty simple. You got to like learn coordinates and dynamics together, and at least for me personally, and you don't have to agree with this, that's okay. I think we should actually have quite a bit of diversity of opinions. But parsimony is the ultimate physics regularization tool here. That is what drives the entire discovery process. It's in this blue region, we're just going to enforce parsimony, really interpretable models, lowest number of terms and dimensions. And that's how we regularize this ill-posed problem and allow sort of this discovery process to happen in an automated way. And I'll stop there and take questions. Thank you, guys.